All right, so in this video, we're going to look at how to do a procedure called change of variables in just one variable. There's another technique for doing change of variables when you have two or more variables, but that's a multivariable calculus thing that we will save for another time. Now, change of variables typically is a technique that is taught often at the end of the chapter on substitution, but it's only sort of somewhat related to the idea of substitution. The things that you make the substitution for aren't the same, and the way that you go about like doing replacements in your integral are not the same. And so they're, conceptually somewhat related. You're trying to change out your integral for a different integral that's easier to calculate and which you can then, remake at the end to get back to what you wanted to end up with. But the change of variables technique is not used when there's a chain rule involved. There's no chain rule involved in this problem. If I take the derivative of x minus 3, I'm not going to get x squared, and I'm not going to be able to get any part of this integral by taking the derivative of any other part of this integral. So these are two functions of x here that are not related in terms of being the result of a chain rule process. They're just two functions. Now, this change of variables won't necessarily work in every case, but it does tend to work particularly well when you have two kind of algebraic functions paired together, typically some kind of a radical and some kind of a polynomial is the sort of most common circumstance. Now, this problem, once you learn integration by parts, you can also do this problem using integration by parts. There are only a handful of integrals that like really yield to multiple techniques where you can apply more than one. A lot of integrals, you can only do one thing to them, and in order to get an answer, otherwise you'll go in circles or you'll end up not getting anywhere. It just doesn't apply. But there are a couple of them where ones like this, where you can actually apply more than one technique. But we're going to apply change of variables to this particular problem. Now, the thing about change of variables is that typically a procedure that works really well is to take if you have a radical in the expression, to take the radical and make that the thing you are substituting a new variable for. So we're going to say that u is equal to the square root of x minus 3. Now, this procedure will work if you just take x minus 3, but the algebra will be a little bit easier if you take the square root of x minus 3. You will get larger powers, but you won't have to deal with fractional powers until you get to the end. So this is one of those things where you have some choices, and sometimes those choices can make things seem more confusing. But I would recommend for a problem like this that you take the radical. So it can be a square root, it can be a cube root, whatever kind of root you have, take the root with the substitution, the change of variable that we're doing here. Now, where this differs from substitution is that I do not now take the derivative of this. I actually have to solve for x and then take the derivative, because I'm not going to have the derivative of this function in this problem, but I do need dx. And so I need to make my dx, I need to make my x naked, so to speak, by itself in order to substitute both for the x squared and for the dx. So I'm going to square both sides. U squared is equal to x minus 3. And then I am going to move the 3 over. U squared plus 3 is equal to x. Now, if I need x squared, then I can just square this expression. And if I need dx, I can take the derivative of this expression, and I'm going to get 2u du is equal to dx. And at this point, I have everything I need in order to substitute into my integral in terms of u. So x squared, this is x. So x squared is going to become u squared plus 3 squared. And then the radical is u, and then the dx becomes 2u du. And now everything is in terms of u. So there's no more x's. And now this is just a polynomial. I'm going to have to do a little bit of algebra in order to distribute this out, but I am going to be able to do my integration now without any difficulty. So let's do some arithmetic. Let's see if I FOIL this out. Oh, I need my integral. That would be nice. If I FOIL this out, I get u to the 4th plus 6u squared plus 9, and I'm multiplying it by 2u squared because there's a u there and there's a u there, du, and then if I distribute, I get 2u to the 6th plus 12u to the 4th plus 18u squared. Yes, that's a square. Du. Just double check. 12, 18. Okay. And then I just do my polynomial power rule. And I get, so I increase this by 1 and I get 2/7 u to the 7th plus, let's see, that becomes a 5, 12 over 5 u to the 5th plus, and this becomes a 3, and so then I divide that by 3 and I get 6u cubed plus c, and then I put my u back, and my u was the square root of x minus 3. Remember, the square root is the 1/2 power, so this becomes 2 over 7 x minus 3 to the 2 over 7, or sorry, 7 over 2 power. Because it was the 7th power, and now the square root makes it a 7 over 2 power. And then 12 over 5, and this is x minus 3 to the 5 over 2 power. 5 because it was 5 originally, and over 2 because of the square root. And then 6 x minus 3 to the 3 over 2 power. Again, 3 from the original u and the 1/2 from the square root plus c. Now, if you do this problem by change of variables versus integration by parts, your original problem will look slightly different because it will be distributed slightly differently, the procedure, but the answer you get will be algebraically equivalent. And in fact, if you have it to compare the other method, the integration by parts method, you can factor out things and make this expression and the expression you get from integration by parts, you can make them look absolute algebraically equivalent. It's kind of messy. Another strategy that you could use would be to graph the function, put this into a calculator like Desmos, and then put the answer you get from integration by parts into the same graphing program and just compare the graphs, and you'll see that they plot on top of each other. They are exactly the same. In principle, they could differ by a constant so that they have the same structure, but they're shifted up and down by the same constant. But in practice, the plus c tends not to be a factor. All of this tends to simply just be algebraically equivalent to what you get when you do integration by parts. So this is a strategy, but again, it's a little bit different than substitution. It has some similarities, but there are some key differences in that in substitution, you generally don't take the powers, you just take the simpler function. In here, you can take the square root. In fact, it makes the math a little easier because you don't have to deal with the half powers while you're doing this integration. And then you have to solve for x, which is not something that you do in substitution, and then find dx. So again, you're not working with chain rules. You're only working with basically algebra pieces. And then you get finally just a way of getting around the fact that these functions are related to each other, but just not via the chain rule.